Hey guys, welcome back. This video we're going to do a quick review of Aqueous Equilibria, right? And this means that it's a solution in water. So to recap, right, the solution, there's a solvent, right? And that solvent would be H2O, right? And for our situation, right, we want to define solvent as the major component. Right? It is what does the dissolving. All right? And it's not in equilibrium, constant expression. All right? So the solvent is the major component of the solution, right? We're going to do a lot with water, especially in Gen Chem 2. Then you have the solute. All right? And this is the minor component. What is dissolved? All right, so the two types. What are the two types of solutes that we're going to talk about? First type and second type. All right. So remember, if we had a solution, let's just talk about this solution. So we have a beaker here, and in here is a solution. All right, that's our solution. If we had two electrodes in here, you know, alligator clip, and then, you know, voltage source, to a resistor of a light bulb or something, and then plug back in here. We want to know, does this get on dim? Is it a dim light? Is it a bright light? Or is it no light? That's the options, right? And so if the light's on, right, it conducts electricity, it's electrolytes. And if it doesn't conduct electricity, it's a non-electrolyte. And so we got, we'll do no conducting. Oh, sorry. Backwards. How about conducting electrons? And then non-conducting. All right, that's from Chem 1. Now, we now know that we have complete. Well, no, let's just not go there yet. Let's talk about the non-electrolytes first. So, because they're non-conducting, we now know that there is no ionization or dissociation of the particles, right? So what are these? These are solids, liquids, gases, molecules. Right? So anytime you see S, L, G, the G, right? Molecules like sugar, like proteins, right? I'll write that down. Sugar, protein, lots of them. They are non-conductors, okay? Electrolyte, there are two types of electrolytes. All right. So we're going to have a strong electrolyte and weak electrolytes. So strong electrolytes have near complete or complete ionization or dissociation. All right. What does that mean? Right? Depends on how you define it. All right, not a big deal. We're going to treat them the same. And so, for example, HCl, we're going to say that 100% goes to H plus and Cl minus. All right. That would be a complete ionization or dissociation. And of course, weak electrolytes have incomplete. All right, they don't. All right, so what are these? Now, one thing we learned, strong electrolytes, K is large. Usually it's much, much greater than 1. And for weak electrolytes, K is small. Usually it's much, much less than 1. All right. So let's talk about what constitutes these. So for strong electrolytes, you have strong acids. All right. What are your strong acids? HCl, HBr, HI, right? So hydrochloric, hydrobromic, hydroiodic. Sulfuric, nitric, perchloric, and chloric. Those are our strong acids. Now, with this one right here, sulfuric acid, note, only the first H, right, is strong. All right, so only the first one's strong. All right, not the rest of them. Then we have weak acids. And this will be all others, unless told. Because obviously there's more than 6 strong acids. I used HPF6 in grad school. Not one you need to know, but it was a very strong acid. All right? And so what do we mean by this? This would be like HF, CH3, CH2. Well, no, that's CH3COOH, H3PO4. And the list goes on and on and on. HCN. Now, remember, just because it's weak doesn't mean, what does that mean? That means H and Cl break up. H and Br break up. H and NO3 break up. H and F doesn't necessarily break up. H and CN doesn't necessarily break up all the way. Most of them don't. However, these two are way more deadly than most of these. All right? Okay, so just the dangerous factor is not what that is. It's about how they react, maybe how fast they react. Typically, the strong acids react faster because one bond's already broken. But those are weak acids. And then we have strong bases. Now, the species are strong bases. We've had hydroxide, so hydroxide and water. Oxide is also going to be one, and sulfide. Those are your strong bases, all right? So typically, we've had lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium, and cesium or cesium, however you want to say it, hydroxide. All right. One that's been there that's not a strong base, all right, it's not, would be beryllium hydroxide. That's not a strong base, all right? And then we have, of course, magnesium hydroxide, calcium, strontium, and barium. The last, period 7, francium and radium, we're not going to do because those are radioactive. That would be bad to use. Now, the most common bases, of course, are that one and that one. Okay? Probably the most common base of all is lime. It's used, raised soil pH, right? Because it's oxides. So how does that work? Well, you have CaO, right? Plus water. Think of it as, right, when that O breaks up, you get Ca2 plus you would actually end up with 2 hydroxides because you get O2 minus, and this guy right here, right, all right, proton acceptor. So O2 minus plus your water gives us OH minus and OH minus. So it technically gives you, this would actually be 2OH minus here and not the O2 with the water, right? That's really what happens, okay? And we'll talk about that later on. Now, going back to the strong bases, rubidium and cesium are too dangerous, all right? And then these guys, well, the group 2 ones are less soluble, right? They're typically less soluble. They don't dissolve well. So we like sodium and potassium. They dissolve well. They react 1-to-1 with hydroxide, so the mole ratio is nice. And so those are our strong bases. But the species that are important are hydroxide, oxide, and sulfide. Now you have weak bases. Of course, it's ammonia and its derivatives. We will expand on this, but anytime you have nitrogen, right, that is the weak base. Right here. That's your base. That lone pair. All right. And then the last thing we're going to have is salts. And these are soluble ionic compounds. So anytime it's ionic and aqueous, right? It's a strong electrolyte. And so when we are writing equations right now, a lot of times from now on, we're going to use net ionic equations. Right? Net ionic equations. We like to use those. All right? And what we do is we write every species as it predominantly exists in solution. All right? What does that mean? So strong electrolytes. Those are ions. Weak electrolytes. Those are molecules. And then we got anything not in solution. All right. So this would be insoluble salts. All right. Gases. It's molecules or formula units. And so that's a little recap from Chem 1 of our Aqueous Equilibria. All right. And so we will be doing this from now on. If you have any questions, reach out. And we'll see you in the next one, guys. Take care.